All right, here we are in example 4, the final example of 8.1. This is Gabriel's horn. It's called, because it looks like a horn, the surface that we generate. Determine the volume and the surface area. So two things we need to do here. Of Gabriel's horn defined as the solid that's obtained by rotating the region R, and they tell us what R is, about the x-axis. So this is a fancy way of saying it's the set of all points, xy pairs, where the x value is just x, and the y value is whatever 1 over x is. So this is a fancy way of saying rotating the graph of 1 over x. The x value is x, the y value is 1 over x. And doing this for all values of x that are greater than or equal to 1. So if we draw this graph, 1 over x, of course, looks like this. This goes up to infinity. It's got a vertical asymptote at x equals 0. But let's call this value right here x equals 1. So if we were to rotate this about the x-axis, then this would sweep out some shape that looks like this. Our cross sections are all circular. So we'd have this sort of trumpet or horn. Okay. So let's go ahead and just do the recap on a volume. Let's do that first. So notice that this doesn't tell us to stop anywhere. So we're actually going to find the volume of this infinitely long solid. Okay. So we would want to use the disk method because our region that we're rotating about the x-axis does in fact touch the x-axis, our axis of rotation. So the volume would be pi times the integral from start to finish of our radius squared dx. So for us, our bounds are 1 to infinity, and our function is 1 over x. So the radius squared is 1 over x squared dx. All right. This is, of course, an improper integral, so we can replace infinity with the parameter r and use a limit mechanic to take r to infinity. I'll rewrite the 1 over x squared as a x to the negative 2. So it's easier to integrate. So integrating, we should have adding 1 to the exponent to get x to the minus 1, and then we divide by that new exponent. So 1 over negative 1, x to the negative 1, between 1 and r. So easy integration here. This is negative 1 over x from 1 to r. And just like when the bounds are in front of the integral, if we have a negative sign, we can flip the bounds. Well, we can also do that after we've removed the integral. It's really the order of plugging in it's what that minus sign affects. So I could absorb this negative into these bounds and flip them. So instead of from 1 to r, it would be from r to 1. So let's do that here. I'll erase that negative, and I'll make this that. Okay. So evaluating now, this is 1 minus 1 over r. Of course, as r goes to infinity, 1 over r goes to 0, so the volume of the solid is actually pi. So this is an infinitely long solid, yet its volume is finite. Okay. Let's go ahead and do part 2, which is to determine the surface area. All right. So for the surface area, we need our function. So f of x equals 1 over x squared, or I can write it as just x to the negative 1. Or, yes, x to the negative 1, I mean. Not x squared, I'm sorry. So we'll take the derivative, and then we'll get our negative x squared. And then we'll square things to get positive x to the negative 4. And then we'll add 1 to things to get that. All right. So for this one, we can now set up our surface area integral, which is 2 pi, the integral from 1 to infinity in this case, our function, which is 1 over x, times the square root of our function. Well, not of our function, but of our derivation right here. So this is going to be the square root of x to the negative 4 plus 1 dx. And that looks absolutely disgusting. So first thing I'm going to do before I try any integration techniques is I'm just going to hopefully make this look a little bit nicer with some algebra. So really, x to the negative 4 is 1 over x to the 4th. So when we add 1 to it, we can get a common denominator here and make this look a lot nicer. The inside of the square root would become x to the 4th plus 1 over x to the 4th. And then the bottom is a perfect square. Right? The bottom is x squared. So then this will become an x squared, but then I already have an x in the bottom here. So combining these two, I should have an x cubed in the bottom. So this should become 2 pi, the integral from 1 to infinity, square root of x to the 4th plus 1 all over x cubed dx. Okay, that looks a lot nicer, but it's still not great. So you may be able to do some integration here directly and calculate this, but that's not the point for this problem. What we're going to do is, instead of trying to find what the actual volume is, what we're going to do is figure out whether or not this improper integral converges or diverges. So what I'm going to do is examine the integrand. So imagine pulling out that integrand so that you can mess with it. Now, it would be really nice if this plus 1 just weren't there. Because if this plus 1 weren't there, then I have the square root of a perfect square. I could take the square root of x to the 4th and get x squared. And then I'd have x squared over x cubed, which I can then further simplify into 1 over x. Okay, so what happens if we get rid of the of the plus 1? Well, if I get rid of the plus 1, that's in the numerator, then I'm effectively making the numerator smaller, right? If I compare this quantity with the plus 1 to the same exact quantity except without the plus 1, then the quantity that I have here with the plus 1 covered up is smaller. So if it's smaller, I'm going to put this to the left of and just put that inequality, less than or equal to. If I get rid of the 1, I make the numerator smaller, and when you make the numerator of a fraction smaller, you make the fraction itself smaller. And since our bounds are 1 to infinity, all of our x values are positive, so I can say that this is in fact also greater than or equal to 0. And if you've watched the previous videos and you're following along in order, you'll know where this is headed. We are trying to build an inequality that will allow us to use the comparison theorem. Okay. So before I actually, let me backtrack a moment and take this inequality, move it down a little bit more. I'm going to simplify this expression into x squared over x cubed, which simplifies further into 1 over x. All right. So really, the important parts of the inequality are this. Because there's a lot going on in this compound nested inequality. So what's really important for the comparison theorem is that we have two functions that are non-negative, which these two are, and that we know which one is greater than or equal to the other, which we have. Okay, now that we have this inequality, notice that the function that we are effectively going to compare our integrand with is this 1 over x. And we know that is good to work with because it is a p integral and we know the behavior of p integrals. So, off to the side here, I'm going to start my little proof. Or maybe below this, actually. Since we have this inequality, so since that inequality is true, and the integral from 1 to infinity of 1 over x dx diverges. Why does it diverge? Well, p is equal to 1, which is less than or equal to 1, which that's the condition for divergence for p integrals. So it diverges. So since the inequality and that integral diverge, so must the integral from 1 to infinity of square root of x to the fourth plus 1 over x cubed dx by comparison. So this is a really strange and interesting example of mathematics. It's famous for this reason. It is a mathematician discovered, or I'm not sure if it was actually a mathematician, but somebody playing around with this at least, discovered that the solid that you get from rotating this particular graph about the x-axis results in a solid that has a finite volume, yet its surface area is infinite, which is very counterintuitive. So that's why it's a really famous example.